waves and have worked out the first set of questions which I have sent across also. Today morning I have sent you the answer key for the DPP type of questions also, or the set 1 questions which I have sent. So you can just go through those answer keys and verify your own solutions. And of course, some of the questions we'll be discussing in class also today. Yeah, so Ganesh, you have some doubts in the sheet. So can you just tell me which questions you have doubts in? So let's start with the doubts in the worksheets. Question 4 of sheet 3. Okay, I'll just get to that. Okay, so let us go through this question. So it says the equation of a plane wave is given by this relation, and we have to find it is incident on a boundary between two media beyond which the wave speed becomes doubled. Okay, so state boundary condition, find the equation of the reflected and transmitted waves. So you can assume in this example that there is, let us say, a heavy gauge string like this, and then on the other side of it there is a light gauge string. Now it is given that if a wave is propagating at a speed v1 in this, it is propagating the transmitted wave or whatever is propagating at v2 in this, it is given that v2 is double of v1, right? So given that, first of all, the incident wave, so that will have a y incident of, the equation given to us is 0.02 sine of 2 pi into 10t minus 5x. It's traveling along the positive x direction. So you can see that this has frequency equal to 10 hertz. It has wavelength equal to 1 by 5 meter or 20 centimeters. And therefore it has a speed v1 because it's in that medium. So lambda 1, f lambda 1, so that is 2 meters per second or 200 centimeters per second. Now it is given to us also that v2 is equal to double of v1, right? X, y are in meters, t is in second. Okay, so wave speed becomes double. So that becomes 4 meters per second. So the frequency on that side will remain the same, 10 hertz, but the wavelength will also become double. So it will become 40 centimeters or 2/5 of a meter. So like that. Now we have to find, take x equal to 0 as the boundary and find the boundary condition on it. So x equal to 0 is the boundary. So if this is the incident wave, then we can see that the reflected wave is, let's say, y reflected is some E1 sine. Okay, so this omega is, how much was it now? 20 pi radians per second, and K1 is 10 pi radians per meter. Okay. So it will be the same omega t plus same K1x plus some phase constant, suppose y1. Okay. So now at the boundary, which is x equal to 0, the incident wave is creating pulses at the rate of that E naught sine of minus k1x. So the reflected wave at x equal to 0 is creating at the rate of E1 sine k1x plus phi1. Now what should happen here is that since the boundary is soft, that is the medium on the other side is lighter. How we know this? Because V2 is greater than V1. So in fact, we know from this information that if this has mu1 and this has mu2 and they have a common tension T, okay, so we know from this information that since V2 is twice, so this is also telling us that V2 is twice of V1, sorry. So that implies that in terms of mu, the relationship is what, that mu2 is equal to mu1 by 4. So 4th in helium mass density, okay, because tension has to be common. So it is a soft boundary. Therefore, the incident and the reflected waves should have same phase at x equal to 0. So that means sine of minus k1x should be equal to, oh sorry, I have written ulta. I should have substituted x as 0. I have looked at the wrong equation, is it, Nina? This is, let me see. No, this is sheet 3, question number 4. Just a minute. We have to substitute x as 0 now. So when you substitute x as 0, your incident wave becomes what? It becomes this omega t, just not minus. And the reflected wave becomes again omega t plus phi. So my mistake. Okay. So this omega 1 t term has to be equal to omega 1 t plus phi 1. So phi 1 in general is like this. So we'll take 0 as well. Okay. So therefore the reflected wave will become some a1 sine, not omega 1, in fact it's just omega, the common value of omega, which is 2 pi f. The common value of omega. So this should be just that kind of term, 2 pi into 10t plus 5x, okay, where a1 is unknown. Now similarly, the transmitted wave that should become a2 into sine of 2 pi into same frequency, okay, but the angular wave number 1 by lambda will become double. Okay, so this will become 5 by 2, so minus sign, it's traveling in the same direction. It will be in the same phase as the incident wave. It will be like this, or a2 sine omega t minus k2x, where k2 is 2 pi by lambda 2. and lambda 2 is nothing but 2 times lambda 1. So hence like this. Okay, so this is the equation of the reflected wave. This is the equation of the transmitted wave. नहीं ओमेगा बाई के होता है ना बेटा, वेव स्पीड इज ओमेगा बाई के और एफ लैम्डा. So V is equal to omega by k or f lambda. So V1 by V2 is equal to K2 by K1 is equal to lambda 1 by lambda 2. Okay. So if V2 is twice of V1, it means that lambda 2 is twice of lambda 1. That also means that K2 is K1 by 2. Right? And dimensionally also you can understand K is length inverse का dimension. हाँ, so K half हो गया ना बेटा. Velocity double हो गया है, so K will become half ना. What is that? So this, see here, this is showing you that your lambda 2 is 2 by 5 meters or 40 centimeters. Okay. Whereas your K1 1/5 of a meter or 20 centimeters. Correct now? So is that all right, Ganesh? That's fine now. Okay. So that is done. Now the only thing is we have to find A2. A2 is the unknown quantity. So as you know, you have the two equations. So you have power conservation. So that will give you the equation that power of incident is equal to power of transmitted plus power of reflected. So half square root of t into mu1 into omega square a naught square should be equal to half square root of t mu2 into omega square into e2 square plus half square root of t mu1 again into omega square into e1 square. Now you know that mu2 is equal to 1/4 of mu1. Okay. So that is telling us that e naught square is equal to e2 square by 2 plus e1 square. So that is your first equation. And you have continuity equation. At junction, because you know that the threads do not break at the junction. So y at x tending to 0 minus should be equal to y at x tending to 0 plus. Okay. So limit x tending to 0 minus y incident plus y reflected should be equal to limit x tending to 0 plus y transmitted. So again, that will show you that E naught sine omega t plus in this case E1 sine omega t. Or if you want to write the limit properly, you can do that also, but the next step will give you this. I'm just showing you all the steps here now. So it's actually unnecessary. Once you get used to this type of question, you can directly write this. This is minus E1x plus E1 sine omega t plus K1x, but same no phase difference. Okay, so on this you have to put the limit that x is tending to 0 minus. And on the other side, that thing should become equal to limit x tending to 0 plus. Yeah, I'll come to that, but let me finish this question. T2 sine omega t minus K2x. But this K1, K2 will not matter, no? Because we are substituting x as 0. So E naught sine omega t plus E1 sine omega should be equal to E2 sine omega t. So the second equation becomes that E naught is equal to E2 minus E1. So best way to do this question is actually you can square the second equation and compare it to the first one, or whatever. I mean, substitute E1 as E0, E2 minus E0 in the first one, and just solve for it. Okay, so I've sent you. No, phase inversion नहीं हो रहा है ना बेटा, because it's, see, that is the whole point. So मतलब यहाँ पे phase inversion क्यों नहीं हो रहा है? Because of this reason. Where is it? Soft medium. Yes, this one. So here you will understand what is happening. The boundary is soft. Okay. So the should be in phase. The reflected, there's no phase inversion. For reflected. Yeah, Ganesh, it's a little bit tricky, so one has to get used to these equations. So this is the only tricky type of question out of what we discussed now. Rest of the things are more or less, very standard. You can substitute in formula-based things. Just about the energy transmission also, you just need to understand the delocalization of energy. But once you understand it, there's nothing difficult in solving. You have to just use the average power formula. Yeah, so this is a JEE advanced type of question. So as you get used to this, you'll be able to skip some steps. मैंने यहाँ पे बहुत detail में समझाया है. You'll be able to skip these steps. You'll be able to directly write. So what we'll do is steps in this type of question. One is you will look at reflected waves phase. That's one thing you look at. Then the next thing you will look at is the lambda 1, lambda 2 or K1, K2 terms, okay, from V1 is to V2 ratio. Okay, so that you know that. And then you will write the power conservation equation and you will write the continuity equation. That's it. No, there's no energy converted to sound or heat over here. There's zero dissipation. You conserve power because there's zero dissipation. If you assume that there is energy converting to sound and light and all that, heat, etc., then we cannot write this power conservation equation. We are taking a simple model of transverse waves along a string, where we assume that the power transmitted remains uniform. There's no dissipation of energy. Otherwise, the amplitude will keep decreasing. It will keep decaying as the wave progresses. Like you have in this thing, damped oscillation. So in real life, there is no such thing as simple harmonic motion. It's always a damped oscillation. But if the damping coefficient is very, very small, then you can assume for at least a certain period of time, it's more or less like a perpetual oscillation. So similarly over here, we'll assume that the dissipation is happening at a very, very slow rate. So we can ignore it at least for the first few seconds or a minute or so, or something like that. Yes, and in that we deduce that because the speed, correct. So as I've written the explanation over here, because of this is the explanation. Medium on the other side is lighter because V2 is greater than V2. That's right. Right. So this is clear, people. So that's why I've given you actually a couple of questions which have. There is one more question, I think one MCQ question where you have to just find the relationship in terms of UT and all that. So that you practice writing out these three equations fast, and then you get into a stage where you don't have to write so many steps. You'll get fast at doing this. You'll just see that, okay, the incident wave. So, at the exam level, when you practice all this, you just have to do this. You can see that the incident wave is E0 sine omega t minus k1x, suppose. Okay. So the reflected wave will be will be A1 sine omega t plus kx if it is a soft boundary, or it will be omega t plus kx plus pi if it is a hard boundary. Okay, so that's done. And the transmitted wave will become A2 sine, same omega but different k and traveling in the same direction. So, this, okay. So now, so that's one step. You've written this. Now power conservation. Okay. So you have square root of mu1 a naught square plus a1 square will be equal to square root of mu2 into a2 square. So that's your next equation. Get used to this. Those common terms cancel out. Okay. Yeah, Ganesh, I'll keep sending practice sheets. Don't worry. Okay. Plus, I'll send some subjective questions also, apart from the ones I've already sent. Okay. So that is your power conservation equation, and then we have the continuity equation. So continuity equation will tell us that your E naught sine, or basically you'll get used to this, that this is E naught plus A1 is equal to A2 in the case of soft boundary, and this will become E naught minus A1 equal to A2 in the case of hard boundary. That's it. So at exam level, you will just get used to solving by these equations. Basically, you have to concentrate on this equation and this equation. So just go through a couple of questions. One I have done in the last lecture, and then this homework one which I have given, etc. The thing is, you will not find too many questions like this in HCV or the standard reference books and all. So that's why I'm giving you some extra questions in waves also. You'll find good questions on other things in waves, but in this particular type of question, you will find less number of questions. Anyway, so this is done. Now, I also had one more request from somebody. Yeah, Suthir, sorry, Sushruth, worksheet 2, question number 5 and 6. Okay, so let's come to that. So worksheet 2, question number 5. Okay, yeah, so this is also a very important type of question. And again, this type of question, we have to develop some shortcut tricks. Otherwise, it becomes very lengthy to solve. So at this stage, don't worry. You just concentrate on solving the question. But as we go along, I will tell you the tricks also. So worksheet 2, question number 5. I'll just go through it, all of you. So it says a plane transverse wave is propagating in the direction making 30 degrees with a positive x direction. Okay. So if this is your positive x direction, now what is happening? Our direction of the wave is like this. This is the axis along which the wave is propagating. So let's say this is some x prime axis, which is making an angle of 30 degrees. So our wave is propagating along this direction. So the equation of the wave will become, like kx prime minus omega t, some function of kx prime minus omega t kind of thing. Anyway, so it's still a one-dimensional wave, so nothing worrying about it. Now the phase difference between points 0, 0, 0. So there is some point, let's say, which is, let's say, this point, which is 0, 0, 0. And this is, there's some other point here. Which is 1, 1. Now, don't worry about, whether this point is lying on this line or not, because it's three-dimensional. So you're understanding my point. I can draw my x prime axis to the point B. You can see that this vector EB will make an angle of 30 degrees with, let's say, this kind of a vector. You see, the vector EB is I cap plus J cap plus K cap, and the vector EC is equal to I cap. So what is the angle between them? Cos theta is 1 upon, so this is not lying on this. Wait. No, I think there should be some correction here. This point should be such that it makes an angle that because this point is definitely lying on this one. So we want this to be half now. Whereas here this will come as √3. We'll have to make some kind of a correction. This point is actually not lying on this line. Anyway, so I'll tell you what the sense of this question is. This is not with respect to one-dimensional wave. This is more with respect to, suppose we have this kind of a situation. We have this question is a bit more complex than just this. So suppose this is our x-axis, and we have a continuous set of waves which are traveling in this direction. So like we have parallel waves traveling like this. Understanding the point? It's a bit like electric field lines and equipotential surfaces. But imagine, there's something like this that you have, for example, क्या होता है that ऐसा केस कब बनता है? Like suppose you have, circular wave fronts on the surface of water. So these are the radial waves that travel like this on a water surface. So though two-dimensional waves in detail are not in our syllabus, but this kind of thing we can discuss. So these are radial waves, transverse, traveling tangentially on a water surface from a point source. So in any direction, if you take your radial unit vector as r cap, the equation becomes something like this, that the transverse displacement is some amplitude into sine omega t minus kr, where r is the radial distance from the point source. So the point source is S. Within diagram, this diagram would be this point source. So from this, okay. Now, when you take r very, very far away, so r tending to infinity, what happens? Those wave fronts, which are circular, they now become plane. So these radial lines, as r tends to infinity, they become this. So these circular wave fronts, very far away from that source, so r tending to infinity, the radial waves tend to become parallel waves. And accordingly, the circular wave fronts, they become parallel waveforms. So यहाँ पे ऐसा कुछ हुआ. Okay, so we are assuming something like that is happening. Okay. So that is why this question is a little bit more complex. So these are traveling waves. These are so-called plane transverse waves, or parallel waves. So plane means that the wavefronts are like this. So the wavefronts are like this. This is just like that question of equipotential separation. So imagine this is in three-dimensional space, and you have the 2 points O, which is 0, 0, 0, and the point E, which is 1, 1, 1. Okay. So now what you have to do is you have to find, so that the vector OP is I cap plus J cap plus K cap. Okay. Now you have to find, okay, the projection of OP along the direction of the waves. So that is going to be, let's say, our delta x prime between the 2 points O and P, because this axis we are taking as x prime, which is at 30 degrees. So we can take a unit vector along x prime, unit vector along the propagation of waves, let's say as I prime cap. So that will become how much? That will become cos 30 I cap plus sine 30 j cap. We can take it like that, as if you know that vector is actually lying in the xy plane, okay, at 30 degrees to this. So it will become root 3 by 2 I cap plus 1 by 2 j cap. So this is your I prime cap. So now our delta x prime will become the projection of OP along this. So it will become OP vector dot product with this. So it is I cap plus j cap plus k cap dot product with root 3 by 2 I cap plus 1 by 2 j cap. So that is becoming how much? That is becoming root 3 plus 1 by 2, assuming in meters. So that is delta x prime. So now if your phase difference, so if your wavelength is lambda, then at the point O, you have some equation y equal to, or whatever, the transverse displacement. We just write that as, in this case, the displacement is happening along the z axis because the direction of propagation is parallel to the xy plane. So this is transverse displacement along z axis. So that at a point is some amplitude into sine omega t minus k x prime, where x prime is along that x prime axis. So any 2 points which are at certain distances, the phase difference between them between O and P will be nothing but k into delta x prime. So that will be the phase difference. So the phase difference will become 2 pi by lambda into that delta x prime. So I think lambda is given to us in the question. If I'm not mistaken, lambda is so Shruth, what is happening here is you don't have to take the projection of that point on the xy plane. The waves are parallel to the xy plane in that direction. So lambda is 1 meter, and this delta x is 3 plus 1 upon 2, I think it was. this will become the phase difference. So you have to think three dimensionally. मतलब ये मैंने XY plane draw किया है, ये XY plane draw किया है, but the waves are traveling, you know, in the XY plane, but parallelly everywhere. And now the point P is not lying in this plane. The point P is lying above this plane. So you're joining that origin point with some three-dimensional point, which is not lying in this plane. And that vector is OP. अब उसका projection क्या करना है मुझे इस x prime axis के along निकालना है. You understand? So you know, three-dimensionally what is happening is let's say so this is y, this is z. Sorry, this is x. So three-dimensionally what is happening is the point P. So this is the origin. The point P is lying somewhere here. So this is your vector OP. But we have to find its projection along which axis? We have to find its projection along this x prime axis, which is lying in the xy plane. So we have to drop this perpendicular and find this. So that is a minimum. So I'll just leave you to note down some of these points because this is a more complex question in terms of understanding. We will understand more and more about these things as we discuss about superposition, and also as we come to later to sound also, because this kind of thing becomes more pertaining to sound actually. If you have a point source of sound, and sound waves are traveling three-dimensionally in the along the radial direction, creating spherical wavefronts. Here too I have assumed still waves in two-dimensional plane because it's still limited to transverse waves, and transverse waves actually don't travel through three-dimensional space. They either travel in one dimension through a string or they travel through a surface because they require some kind of tension in the medium. So a surface has good Ganesh. It's a tricky question and I'm happy that you worked this out. So yeah, so coming back to transverse waves, transverse waves require some kind of tension in the medium. So that can either be surface tension for a two-dimensional surface of a liquid, or the tensile kind of force that acts along the length of a string or a wire or something like that. They can't travel through a solid, for example, like longitudinal waves or pressure waves or sound waves that we'll discuss later. They do travel through three-dimensional space, whether they are traveling through solid like concrete or rocks, or they are traveling through a liquid or whatever. But transverse waves don't travel like that because the transverse displacement actually requires a tensile force. Like we had seen in the derivation of propagation speed, there was the tension centripetal component was providing the centripetal acceleration for those particles to go up and down in SHM. Now, in a three-dimensional medium, you will see that as you create a disturbance, first of all, that disturbance creates longitudinal displacement. It does not create transverse displacement. So it creates pressure waves. So that whole situation of creating a transverse displacement and that transverse displacement traveling along the medium because of that kind of force, which is creating the restorative force for SHM in the transverse direction, that is not possible in the three-dimensional case. It is only possible when there is some kind of a tensile force involved. So either that is surface tension along the tangential direction to a surface, or it is the direct tensile force along the length of a string. So Ganesh, hope this point is also clear. Okay, so when I come to longitudinal waves and we discuss the whole thing, I'll also want to make this point in more clarity, that why transverse waves cannot propagate in three dimensions. They propagate either on a two-dimensional surface or they propagate on a one-dimensional string or wire or thread or something like that. Okay, so just go through this for a minute and we will discuss the sixth question after this. Yeah, good. You asked the sixth question also, because there also we'll understand that why in principle you should be calculating the kinetic energy by integrating the kinetic energy of all the particles. But we can actually calculate it by just using the average of sine square function. We discussed last time that the average value of sine square function is the same as the average value of cos square function, which is half. So in sixth question, we'll be making use of that. So question 6, we are given an equation of a wave, which is 1 centimeter is the amplitude, and we can see that angular wave number is 2 pi, which means wavelength is 1 meter, and angular frequency is 20 pi, which means the frequency is 10 hertz. X is in meters, T is in seconds. Linear mass density of the string is also given to us 0.01 kilogram per meter, or that's the same thing as 0.1 gram per centimeter. So we have to find the kinetic energy. We want to find the kinetic energy of a portion of a string of length equal to 1 wavelength. So of course, from here you can first of all see that the k, which is 2 pi by lambda, is 2 pi. So wavelength is 1 meter, and you can see the omega, which is 2 pi f, is 20 pi. So the frequency is 10 hertz. So now let's come to this, and you can see that the amplitude is 1 centimeter. So these are the things that will become important. Now if you consider the instantaneous particle velocity, that is del y by del t, that is a omega cos, or in this case minus a omega, because cos kx minus omega, because y was a sine kx minus omega. So now on the string, as this vibration is happening at a distance x, if we consider a sectional length dx, so that particle's kinetic energy is half dm into particle velocity square. So it is half of mu dx into e square omega square cos square dx minus omega t at some instant of time. So the kinetic energy of a certain section, let's say from A to B, will become integration of this. So that is half mu e square omega square cos square dx minus omega dt dx from x equal to whatever that portion is, x equal to whatever it is, from A to B. So it will be this kind of a value. Now in this you have to understand that we are looking at a particular instant. So at a particular instant, let's say t equal to t naught. So this becomes t naught. So this actually becomes a phase term. So basically it is something like this. You end up doing this integration. It is half mu omega square e square into integration of cos square dx plus some phase dx from xa to xb. You are ending up doing this. Okay. So here you don't have to integrate. Now for our question, we should actually take XA as suppose 0 and XB as lambda, such that K lambda is equal to 2 pi lambda. But we don't have to do all that. Okay, so what we're doing is, since we are taking from XB minus XA, we are taking as lambda. Okay, so that means we can write this as half mu omega square A square into cos square function's average value. Okay, cos square theta's average value. But this will of course also get divided by K, because you will be substituting this as theta. No? So that dx by, so you will be substituting, so where theta is equal to kx. So dx becomes d theta by k. That's where one k also comes outside. And cos square function's average, you know, is half, because we are taking one whole wavelength. So the kinetic energy of that portion will become this. And now you can just substitute the values. Is it clear? If you want to do this properly, without the trick and all that, just substitute. So by integration method, by proper integration method, if you want to do it, then substitute XA as 0, okay, XB as lambda, or in this case 1 meter, okay, and substitute your T as 0. So this equation, this would actually become this, that kinetic energy is half mu omega square A square. T को मैंने 0 substitute किया, so cos square kx dx from x equal to 0 to x equal to lambda. Okay, so you'll end up getting what I'm telling you. So now in this you'll have to make that substitution. Substitute kx as theta. So this will go from 0 to 2 pi. So there will also be a 2 pi here. The limits are the average value into the theta is going from 0 to 2 pi. So you can use this trick over here. So ultimately what you will get here is, you will get pi by 2 mu by k into omega square e square. That will be the kinetic energy. And further you can substitute k as 2 pi by lambda. So this will become 1 by 4 into mu lambda into omega square into e square. So basically you can see it is 1 by 4 into mass of that portion. And mu lambda is nothing but mass of that portion. So why we are getting that factor of half? We are getting it as half m omega square a square into half. So this we are getting because this is the average value of cos square function. This cos square theta is half average. So if all the particles were traveling at a uniform speed omega e, it would have been half m omega square e square. But because they are traveling according to the cos kx distribution, so that is why there is a cos square function's average which is coming out as half. So this is the interpret. This is the way to interpret. Similarly, if we had taken a portion of the string only from, let's say, 0 to lambda by 2, then this would have been mu lambda by 2. But it still would have been that, because even in lambda by 2, it has that symmetry, that cos square function has the same symmetry as it has over 0 to lambda. But suppose we had taken 0 to lambda by 6 or something, then we could not use this average value, because this average value is over one cycle. So this thing has to be at least No, half a cycle or multiple of half a cycle or multiple of full cycle. Like that. Are people following this? As I hope you are understanding this trick of using the average value. Okay. Whereas only in very rare cases, if you have a complex type of question where you want to calculate the kinetic energy between, let's say, 0 and lambda by 3 or 0 and lambda by 6 or something, then you have to actually sit and do this integration. You can't get away by using the average value. Okay, so just make a note of the solution of this, because this is another interesting and important type of question. Okay, so I'll just come back to this shortcut trick in just a moment. First, you just write down these steps here. Okay, so let's understand how this actually works. So, oh sorry. Okay, so please, I'll go back to the question. Yeah, I'll explain the integration part. So first of all, let us understand this integration, which we have discussed earlier. Cos square theta d theta or sine square theta d theta. This becomes 1 plus cos 2 theta by 2 d theta, or this becomes 1 minus cos 2 theta by 2 d theta. So you can see that whether we do integration of cos square theta d theta from 0 to, for example, 2 pi, or we do integration of sine square theta d theta from 0 to 2 pi, we will end up getting pi. Okay. Or instead of this, if we do this integration from 0 to pi, we will get pi by 2. Or the same integration from 0 to pi, if we do, we will get pi by 2. You see that if we do the integration, so the reason for this is that the average value of cos square theta is equal to the average value of sine square theta over one cycle, and that is equal to half. Okay, so if we are doing integration of cos square theta d theta from, let's say, alpha to beta, okay, and beta minus alpha is a multiple of pi, we will always get this as the average value into beta minus alpha, or we'll get it as the average value into m pi. And same for this also, sine square theta, we integrate it from alpha to beta such that beta minus alpha, the interval is an integer multiple of pi. So the interval is an integer multiple of one cycle, that is pi. Then the value will be the average value of the function multiplied with the interval. The average value is half and the interval is beta minus alpha. Now in case of sine and cos, this will even work if it is a half cycle. I mean, sine square and cos square will even work if it is a half cycle, because for example, sine square is like this. Sine square theta. So if you see, because of symmetry, therefore average value of y is equal to half from 0 to pi by 2, 0 to pi, 0 to 3 pi by 2, 0 to 2 pi, like this. So it's not only beta minus alpha equal to n pi, but also beta minus alpha equal to n pi by 2. When can be both even and odd, because it's just that symmetry. That function, this part is a mirror image of this part. So the average value of this function is the same. Okay. So that's how we can use the trick. So that is why, for example, if I calculate sine square theta d theta from 0 to 5 pi by 2, suppose I'm doing this. So according to my theory, this should be equal to half into 5 pi by 2. It should be 5 pi by 4. And let's just check out. Okay. Put this will become 1 minus cos 2 theta by 2 d theta, integration from 0 to 5 pi by 2. So that should be theta by 2 minus sine 2 theta by 4 from 0 to 5 pi by 2. So you can see that we get this as 5 pi by 4, because this term sine 5 pi is also 0 and sine 0 is of course 0. So now you can see that this is an odd multiple of pi by 2. This is in fact half cycle of sine square. So it's working. Similarly, let's do integration of cos square theta d theta. Suppose now you take something even a little bit complex, like you take pi by 4, say 5 pi by 4. You do something like this also. Now here also, see what is happening. My alpha is equal to pi by 4, beta is equal to 5 pi by 4. Now note, beta minus alpha is pi, which is one cycle. Okay. So I should get this as average value into the interval. So the average value is half and the interval is 5. So I should get this as 5 value. Okay, because actually what I'm doing here is cos square function sine. It's rounded at the bottom, but whatever. So pi by 2 pi like this. 3 pi by 2. Now here actually I'm calculating the average between these limits. Pi by 4 is here and 5 pi by 4 is here. But in this range also it's symmetric, you can see. It should come out to be that. So anyway, now coming back to this. Now from this, if we move on to, we are doing cos square kx dx. Okay. From x equal to e to x equal to b. Suppose we are doing this. Okay. Now here what is happening is k is equal to some kind of 2 pi by lambda term. Okay. So when you substitute, you will substitute kx as theta. So dx becomes d theta by k. Okay. And x equal to a corresponds to theta equal to 2 pi by lambda into e. And x equal to b corresponds to theta being 2 pi by lambda into b. So this becomes cos square theta d theta by k from theta equal to, let's say, alpha to theta equal to beta, where this term is alpha. So that is why you will see that this term, so if b minus a is equal to n lambda, okay, that means beta minus alpha will become n times 2 pi. Okay. Or if b minus a is some this of lambda by 2, then beta minus alpha will become m times pi. Okay. So in that case, you can again use the average value. So it will become, so if beta minus alpha is multiple of a cycle, or even pi by 2 for that matter, because of symmetry, or that basically means that b minus a is a multiple of lambda by 2, because lambda by 2 corresponds to pi. So even lambda by 4 will be okay. Then this integration of cos square kx dx from a to b will become 1 by k cos square theta d theta from alpha to beta, where this will become 1 by k into beta minus alpha into average value. This will become 1 by k into that 2n pi into half. So you can see that this will become 2 pi by k, which is lambda. So n times lambda into the average value. So this function will become like this. Provided b minus a is n lambda. So this will happen provided b minus a is n lambda. So that is a trick that we can use. Okay, so वहाँ पे क्या हो रहा था? See, we were integrating cos square kx minus omega t dt, so dx. you're doing this integration. Okay. From x equal to 0 to x equal to lambda. Okay. And suppose we are doing it at time t equal to 0. So this became cos square x dx from x equal to 0 to x equal to lambda. So because this limit was a cycle, so we could say that it is equal to 1 by a cos square theta d theta from x equal to 0 corresponds to theta equal to 0. X equal to lambda corresponds to theta equal to 2 pi. So this will become 1 by a into cos square function's average value, which is half, into the interval, which is 2 pi. So this is the truth. This is the cos square function's average value. Okay. And this was the interval. So this whole term became how much? This whole term became half of 2 pi by 2, which is nothing but lambda by 2. So that therefore we got that whole thing. So that kinetic energy was half mu into omega square into a square into cos square kx minus omega t dt integrated from 0 to lambda. So this whole term became this lambda by 2. So we got half mu omega square a square into lambda by 2. Okay. Now you notice that this is half into mu lambda into omega square. Now this mu lambda is nothing but the mass of a section of length lambda of the string. Okay. So it is like half m into that V max square, because omega e is the maximum speed. So again, why this is happening? Because the speed of a particle is V max into that sine or cos whatever kx minus omega. Okay. So the kinetic energy is distributed according to a sine square function or a cos square function. So if we are distributing it over one wavelength, or even for that matter over half a wavelength, because of that symmetry, we can use this trick of using the average value. Okay, so hope this point is clear. It's a pretty subtle point in integration. This is one of the tricks that you can use in doing advanced level questions. So this will work for sine square functions. Sine square kx will be integrate from a to b. This will be the same, provided we have this condition that b minus a is an integer multiple of lambda or lambda by 2. So even if you don't use this trick for this question, you just have to actually work out this integration. You will substitute this as cos square theta by k d theta. Put the limit 0 to 2 pi in this case, and then write cos square theta as 1 minus cos 2 theta. Sorry, 1 plus cos 2 theta. So you can even work out this integration. There's no big deal. From 1 by k, 1 plus cos 2 theta by 2 d theta from theta equal to 0 to theta equal to 2 pi. So you'll get the same thing. You get the value of this integration as 5. Okay, so should I'll come to that question. Just give me a second. No, so Shruti, in question number 7 of sheet 1, no, it clearly says that the left half has linear mass of this much, while the right half has linear mass. So the question language is such that half of the thread which is on the left has one linear mass density, half of the thread which is on the right has a different linear mass density. If it was different, like if it was, let's say, one side was 1/3 and the other was 2/3, then the answer we would have got is different, no? Because it would have been L by 3 divided by the speed V1 plus 2L by 3 divided by the speed V2. So the question clearly asks you to assume that half the thread has one linear mass density and the other half of the section has the other linear mass density. You know, if you change that ratio of lengths on either side, then your whole question will change and the answer will change accordingly. Okay, so I think we can move on now to the next part. Right, so continue working on the problems. I hope you're getting the HC Verma problems also without too much difficulty. And you can continue sending me doubts through the week also. Don't need to be late for the class in case you're getting stuck with some questions and all. So I will be sending you more questions on this section also, even though now we are moving ahead to the next section where we will look at interference of transverse waves. Now the term interference has a very specific definition. So this term is used when, so the term interference is, the definition of this term is that it is superposition of two or more waves. In this case, we are talking about transverse waves, but in general waves traveling in the same direction. And actually, since we are talking about the proper definition, we will use the term coherent, and I'll explain what coherency means. Coherent, and in this case, we'll talk about transverse waves. Traveling in the same direction results in a phenomena called interference. You just write down this definition. So what happens in interference is there is superposition of multiple waves which are having this property called coherence. So what is that? Let's understand what are coherent waves. Coherent waves are waves such that their phase difference is constant. Okay. So in case of transverse mechanical waves, actually not just transverse mechanical waves, all mechanical waves. Or let's say also longitudinal, because when we come to longitudinal, we'll repeat this point. Where it becomes different is actually the case of electromagnetic waves. So that will be when we come to wave optics later. And also longitudinal mechanical waves. If the frequencies are identical, then the waves are coherent. Okay, and I'll explain this point also, how this happens. But right now, you just write this down as a definition. So, interference kya hota hai? It is the superposition of coherent waves traveling in the same direction. And what do we mean by coherent waves? It's waves that are having constant phase difference. Constant means constant with respect to time. The phase difference between the two waves superimposing at a particular point is not changing with time. If that is happening, then we say that the waves are coherent. So we will see that in case of mechanical waves, both transverse and longitudinal, the condition for coherence is that frequency should be identical. So identical frequencies becomes the condition for coherence. So let us understand this like this, that suppose we have that very long string going to infinity, tension P, and now we have two sources. One source S1 is of amplitude A1, frequency F1, and another source here. So it's creating a wave like this. S1 is creating a wave which is traveling with a speed v like this. Now we have a second source also present, S2, which has an amplitude A2 and a frequency F2, let's say, and this is creating another wave which is also traveling with the same speed. Now these two waves will result in some kind of superposition at a point like this, and let us say the distance of that point from the first source is x1, and the distance of the wave from this, or the distance of that point from the second source, is x2. Okay. So in such a case, that if S1 and S2 are two simple harmonic oscillators, creating transverse waves, say y1 equal to E1 sine omega t minus, or omega 1 t minus k1x plus some phase constant phi 1, where omega 1 is 2 pi f1, okay, and k1 is omega by, or omega 1 by v, where v is of course square root t by mu. And similarly, the second one is E2 sine omega 2t minus E2x plus some phase constant phi 2, where omega 2 is 2 pi f2, and accordingly K2 is omega 2 by v. Okay. Then at the point P, okay, the net displacement will become displacement due to y1 plus y2. So you can see that the resultant displacement being the superposition of these will be a1 sine omega 1 t minus k1 x1 हो जाएगा because वो वाले सोर्स से उसका डिस्टेंस x1 था plus phi1 plus a2 sine omega 2t minus k2 x2 plus phi2. Okay, so it becomes the net displacement becomes the superposition of two oscillations, two SHMs of amplitudes E1 and E2, but with phase difference delta phi, we can say. Now that phase difference is omega 1 minus omega 2 into t, okay, minus k1 x1 minus k2 x2 plus phi 1 minus phi 2. So this is the phase difference in general if we take two general sources. So from here you can see that the condition for coherence of waves y1 and y2 is that the phase difference delta phi should be constant with respect to time. So that means this delta phi should not depend on time. So for that to happen, my omega 1 minus omega 2 must be 0. And then your phase difference delta phi is just phi 1 minus phi 2 minus of k1 x1 minus k2 x2, which is just constant. In fact, this will become phi 1 minus phi 2 minus of k into x1 minus x2. Because in this case, what will happen that k1 will be equal to k2 because omega 1 is equal to omega 2. But anyway, the more important thing is the condition is this. This becomes the condition for coherence. Okay. Or in other words, 2 pi into f1 minus f2 should be 0, or f1 should be equal to f2. So this is one very critical thing to understand. In which case two mechanical waves will be coherent when they are superimposing at a point, when their sources are of identical frequency. The condition for coherence is the sources should be of identical frequency. Okay, just note down this point first with the understanding of it, not just that the condition ही होता है, but क्यों होता है ये condition? Because the definition of coherence ही है कि जो superposition of two oscillations हो रहे हैं, वो ऐसे हो रहे हैं कि दोनों oscillation का phase difference not necessarily zero है, but जो भी phase difference है, it should be constant in time. That is a condition for coherence. Okay. So we take a physical example where we are having waves created by two independent sources. In which condition we will say that the waves created by them are coherent? In this condition, that wherever they superimpose at any arbitrary point, they are creating oscillations whose phase difference is constant in time. So the condition for the phase difference to be constant in time is nothing but the frequencies should be identical. Now, obviously, the moment the frequencies become identical, the wavelength also become identical because the waves are traveling through the same medium. So V is equal to F lambda. Or in other words, if omegas are same for both the sources, then obviously the wave number or the angular wave number will also be the same for both the waves. I'll explain to you. Just write down up to this point below first. Okay. I mean, you don't need to write every step in detail. Just understand the points because I'm going to give you the notes anyway. But make sure the mathematical part is clear to you. Okay, just a moment, I'll explain why K1 will become equal to K2. Okay, just come to the last step first. So this is the critical thing. Now we want that at that point, which is at distance x1 and x2 from the two sources, s1 and s2 respectively, the phase difference whatever is coming, it should be constant in time. So the condition for that is that this term should disappear. ये वाला जो term है, phase difference वाला term है, this term should disappear. I mean time वाला जो term है, it should disappear. So omega 1 should be equal to omega 2. Now mind you, the moment omega 1 is equal to omega 2, automatically K1 becomes equal to K2 because we have this relation that K1 is equal to omega 1 by V and K2 is equal to omega 2 by V. So if K1 is equal, omega 1 is equal to omega 2, if omega 1 is equal to omega 2, it implies that K1 is equal to K2. Or another way of saying it, that F1 is equal to F2. It implies that the wavelengths are also the same. You know, booming, that point is clear now. No? So now we will see what superposition of these type of coherent waves results in. Okay. So interference or superposition. Oh, sorry. Okay, just a minute, Sudhir. I will go back to the notes and come back. Right. So let's the next thing to understand. So interference of two waves, for example. So it's superposition of two waves of identical frequencies traveling in same direction, but amplitudes may be different, okay, of amplitudes E1 and E2, and not necessary that A1 is equal to A2. Okay, so this results in a net disturbance or wave of some net amplitude which can be anything in between A1 plus A2 and the difference of A1 minus A2. This you already seen in superposition of SHMs. Okay. And frequency F, okay, where F is the frequency of the original sources. So the two original sources were of frequency F each. Okay. So this A net, now the value of this depends on E1, E2 and the phase difference, delta phi. Okay, so let's see how that works out, how it depends on the two. Okay. So going back to our earlier description, okay, suppose the wave created by the first source was some E1 sine omega t minus kx. Suppose it was this, and the wave created by the second one was E2 sine omega t minus kx plus some phase constant. Okay. So this is by source S1, which is of frequency F and phase constant 0 and amplitude A1. And this is created by source S2 of same frequency F, phase constant equal to some phi naught in relation to that one, and amplitude E2. Okay. So here what happens is omega for both the waves is 2 pi F and K for both the waves is omega by V, which is nothing but 1 by 2 pi F into square root of T by mu, where T is the tension of the string and mu is okay. So now at some point P, okay, if X is equal to X1 from source S1 and X is equal to X2 from the source S2, okay, for that point P, then the net disturbance will become Y1 plus Y2. So that will become E1 sine omega t minus kx1, and for the second one it will become sine omega t minus k into whatever distance there is x2, plus the second source is also having some phase phi naught, let's say, in relation to this. Okay. So we can say that the net disturbance is E1 sine omega t, just a moment. Yes, omega t minus alpha, let us say, plus A2 sine omega t, or let's write this as plus alpha only, okay, plus some beta. Where why I'm writing this is alpha and beta, because they are independent of time. Alpha and beta are constants. So you can see where alpha is equal to minus kx1, beta is equal to minus kx2 plus phi naught. But the important thing is that alpha beta are constants. They are not varying with time. Because that distance x1 is fixed, no, from the source S1, and that distance x2 is fixed from the source S2. So this becomes like this. Okay. Now suppose, so to solve this next, what we'll do is we will use a trick that suppose beta minus alpha is equal to delta phi. that becomes the phase difference at the point P, okay, of the two waves y1 and y2. That becomes the phase difference. So now we can write, in terms of the phase difference, we can write the net as A1 sine omega t plus alpha plus A2 sine omega t plus alpha plus this phase difference delta phi. So we can write beta as alpha plus delta phi, where delta phi is a constant. So this phase difference is constant because they are coherent waves. Okay. So this is the constant phase difference because the waves are coherent. Okay. And now we'll use the simple trigonometry thing. Okay. So you can treat this as this term as theta 1. Okay. Or whatever, you can just treat it like theta. Just treat this term like theta. So you're doing some trigonometrical operation like this. A1 sine theta plus A2 sine theta plus delta phi, where theta is equal to omega t plus alpha delta. So expand this. So this is A1 sine theta plus A2 sine theta cos delta phi plus A2 cos theta sine delta phi. Okay. So why we are doing this is because note that theta is the thing which is changing with time. Okay. Theta is the time dependent part. Okay. Whereas delta phi was constant. That's why we are separating this out. Okay. So keeping the terms of theta separate because theta is ultimately time dependent. Okay. So theta is about the frequency of the oscillation. Okay. So the way to proceed is our normal trigonometry method. So just proceed from there, and I'll just have to reshare the screen once. Okay. Just a moment. So just like you've done in superposition of SHMs, same kind of method. So what I'm going to do is I'm minimizing this so you get an idea up to this step, and then proceed yourself. I will put up the final solution also, but try to proceed with the steps yourself. How you trigonometrically resolve this? So we'll use trigo to resolve this to a single term, which is sinusoidal in theta, where theta is a time dependent thing, omega t plus something alpha. So that alpha doesn't matter. The important thing is theta is a time dependent thing. So that's what we're doing. So first write down this part. Okay. Then we'll come to that. Write down or just make sure you're clear with this up to here. Then we'll come to the steps below. So this whole thing below here, this is what we have to now resolve into a single sinusoidal term in omega t. Yes, it is a phasor sum, which looks very much like a vector sum. So you get that kind of relation, that your net amplitude sum of the, correct, is root of a1 square plus a2 square plus 2a1 a2 cos delta phi, where delta phi is going to be nothing but this term, the phase difference. Okay, so now try to proceed from this point. We have already expanded this in the term below. Okay, so have you written down up to, I mean, are you clear up to this step here? Yes, Sudhir, are you clear up to this step? Actually, you're writing equation of y2. Okay, so let's come to the step above. Okay, so this is all in context of that same diagram we were talking about earlier. That on that string, you have a source S1 over here, a source S2 over here. Now both sources are of same frequency, but different amplitudes. And now we are looking at the general superposition of the wave at a point P like this, which is at a distance x1 from the first source and at a distance x2 from the second source. So the first source is creating some wave y1, the second source is creating some wave y2. Both are traveling at the same speed. So both have same frequencies. So y1 and y2 have the same frequencies f and f. So they are the same wavelength lambda and lambda, where v is equal to f lambda square root t by m. That's how all these equations come. So now at the point P, for the wave y1, we have to substitute the value of x as x1. And at the point P, we have to substitute for the wave y2, the value of x as x2. So that's how we are getting this. Okay. Also, this phase is 0. And this one is starting with a phase of phi naught. So that also we incorporated in the equations. Because while the two sources have to be same frequency, but there's no necessity that they have to be in phase. They could be having some phase difference. Right. So once we have established the equations y1 and y2, now it's just a matter of mathematics, and we have to write the superposition of them. Okay, now try to proceed from the last step further yourself. Right, Ganesh. Good. So you have got that equation of that net amplitude as a phasor sum of A1 and A2. So good. So I'll just show the steps for everybody here. So proceeding next over here, you'll see that we can write this as E1 plus E2 cos delta phi into sine theta plus E2 sine delta phi into cos theta. Now, why we are separating in this way is because remember theta is the time dependent term. It's omega t plus alpha. So it is time dependent. And delta phi is constant. That's right. So now this whole term, we can think of it like a constant, let's say P. And this whole term is a constant, let's say Q. So this becomes a familiar trigonometric equation that y net is P sine theta plus Q cos theta, which is square root of P square plus Q square sine theta plus, let's say, epsilon, okay, where epsilon is tan inverse of Q by P. Okay. Now this term square root of P square plus Q square is a constant because P and Q are constants. So that is becoming a net amplitude. Okay. So a net disturbance at that general point is becoming some net amplitude into sine of theta, which was omega t plus alpha plus some. So these two also we can combine. So we can see that net amplitude is the important thing. Okay. This is some phase term, let's say 5 prime. So the resultant oscillation due to interference. Okay. Epsilon is a constant term. अच्छा ये आपको trigonometry में पता होना चाहिए. Okay, I'll explain. So in trigonometry, what happens is if you have an equation y is equal to a sine theta plus b cos theta, you multiply divide by root of a square plus b square. No. So this becomes root of a square plus b square into a upon root the same plus b upon root of the same. Okay. So then what you do is this term you imagine it to be cos epsilon and this term you imagine it to be sine epsilon. So this becomes some capital A into sine theta plus epsilon, where capital A is root of a square plus b square and epsilon is tan inverse of this divided by this b by a. This is what we talk about. So for example, in trigonometry, you know that if you have a term y is equal to, let us say, 2 sine theta minus 2 root 3 cos theta. So immediately you know that this becomes 4 sine theta plus some epsilon, where epsilon is now tan inverse minus root 3, and in which quadrant you can see, because this term will be substituted as sine epsilon. So sine is negative and cos is positive. So it's which quadrant? It is the fourth quadrant. So your epsilon here will become minus pi by 3 or 2 pi minus pi by 3. That is 5 pi by 3. So that will become 4 sine theta minus pi by 3 or plus 5 pi by 3 like that. So this term reduces to this. So that method we are using over here. That is that epsilon. So this is like bread and butter stuff in trigonometry for you. So if you know this. So coming back here, this is the resultant oscillation due to the interference at the point P, where you can see that omega is equal to 2 pi f, where f is the common frequency of the sources, of the two sources S1 and S2. But the net amplitude now, so tracing back what this net amplitude is, net amplitude is nothing but root of what we had written as P square plus Q square. Now in turn you can see that P we had written as E1 plus E2 cos delta phi, and Q we had written as E2 sine delta phi. So that is where this formula now becomes very important. The important thing in interference is how to get the resultant amplitude or the net amplitude from E1 and E2 and the phase difference. So next step you can see that the net amplitude comes like a vector formula. But here it's not a vector quantity, so instead we call it a phasor formula because it depends on phase. That is the phase difference. Delta. Okay. So this we can also understand like this. That so what we can say now to summarize all this. Okay. So basically what we are saying is that if y1 is E1 sine omega t plus some constant at some point P, and the second one is E2 sine omega t plus some beta at that point P. Okay. So we say that the phase difference between the two waves or between the two disturbances, delta phi, is equal to beta minus alpha, whatever that beta minus alpha is, okay, which is supposed to be a constant when we're talking about interference. Okay. So the net, which is y1 plus y2, actually becomes some net amplitude into sine of omega t plus some net phase term. So in this, the important thing is to be able to relate, the most important thing here is to be able to relate this term with respect to A1, A2 and the phase difference. And that relationship is the one we were just talking about. That the net amplitude is root of E1 square plus E2 square delta. Okay. So the easy way to remember this is what we call the Phasor diagram method. That is, if you represent the amplitude A1 with, like you have vector arrow, like that you have phasor arrow, so A1. And the second one's amplitude A2 is at a phase difference of delta phi with respect to this. So they are not vectors, mind you, over here, but they are quantities which have phase. So the net amplitude becomes this. So this is also an easy way to remember the analysis. Just treat it like phasor addition, and this is actually your epsilon term. So the epsilon term is usually not so important for us, and if we want to calculate it, we can directly do it by adding the two wave equations. So in numerical examples, we'll come to this. So this is the phasor diagram method also. Okay. So just note down these steps first because these are the critical things, and you have to know this whole derivation properly. So this equation we had reduced to this by expanding this term, and then that's how we proceeded below. अरे सुधीर एप्सिलॉन में तो वो कांस्टेंट टर्म है ना बेटा. सी ये दोनों इक्वेशंस को हम कंबाइन कर रहे हैं ना. p sin theta plus q cos theta. तो ये एप्सिलॉन टर्म क्या है? इट इज tan inverse of q by p. Just like I explained to you in this example, this numerical example that I took of a similar equation. So this term epsilon, how it became minus pi by 3? Because it is tan inverse of this term divided by this term. So epsilon is a constant according to that, because p and q are constants. It is tan inverse of q by p, as you can see over here. This term is epsilon. It's a constant. It's a constant phase term. Is it clear now? Okay, good. Okay, I'll show you the example on the right hand side also. Okay. So derivation and all, you can go through the steps carefully every time. That's fine. But the important thing is, from now, this is the working formula for us to find the net amplitude. And the easy way to remember the working formula is through the phasor diagram. So that's a very nice trick to remember this. Okay. So now let us also understand the specific definitions. As a first, you can write down this part if there's anything remaining. Okay. So basically, whatever this term alpha comes as a result of the distance from the first source and the initial phase term of the first source S1, and whatever this term beta comes as a result of the distance from the second source X2 and the phase term of the second source S2, whatever they come, alpha and beta are some constants which we will be always able to work out in the question. And based on those constants, we know the phase difference between the two waves interfering at that point P. At that particular point P, the phase difference is becoming this delta phi. So according to whatever the value of delta phi is, the net amplitude is like this. So you can see from this that the net amplitude can range between a maximum of A1 plus A2 and a minimum of A1 minus A2. Okay. So from this we also understand, similar to triangle inequality in your this thing vectors, its maximum value is this and the minimum value is the difference of A1 and A2. Okay. So this occurs, so when A net is equal to A1 plus A2, that is the maximum possible value. It is called the interference is termed as constructive interference. So within interference, there is a subcategory. Right, this is a separate point in your notes. So when this is equal to A1 plus A2, which is the maximum possible value, the interference is categorized as constructive interference, and the condition for constructive interference that becomes that delta phi should be equal to 2n pi. So that cos delta phi should be equal to unity. So 0, 2 pi minus 2 pi, 4 pi minus 4 pi. So n is 0 plus minus 1 plus minus 1. Integer solution of this. Whereas we can also have a situation called destructive interference. interference, where the amplitude resultant is the minimum. So, whereas for the net amplitude to become the difference of the two waves superposing amplitudes, it is called destructive interference. Okay. The condition for this is that delta phi should be an odd multiple of pi, or cos phi should be equal to minus. So again here n is equal to 0. Okay. So again this is something important, that within interference the two special cases of constructive and destructive interference and their conditions in terms of phase difference. Whereas of course you have a lot of general cases where it's neither constructive nor destructive. So it's anything between the difference and the sum. नहीं, molecular orbitals का वो अलग है बेटा. That is the overlapping of the probabilistic wave functions. But that is not transverse mechanical waves. And there the phenomena that happens, the superposition of the probability waves results in standing wave patterns, not really interference. So it's a little bit different. It is superposition of waves but not interference, and that too not mechanical waves, but rather the the quantum mechanical probabilistic waves, or the Schrodinger wave equations. Okay, so let's understand all this with an example, the typical kind of numerical example. Then it will become clear to you how to solve each of these terms. Okay. So suppose we have that standard situation of ours, that we have a very long stretched string for which the various terms are given to us. So this is so the tension is, let us say, 250 newtons, and the linear mass density is 1 gram per centimeter. This point is x equal to 0. It is actually, when I explain standing waves in the next lecture, maybe we can discuss a little bit about how orbitals can be created by standing waves created by the the Schrodinger waves equations. Okay, but that's a little bit different from interference. Okay. So this is our x-axis. So the tension and linear mass density of the string are given to us. Okay. Now what is happening is we have, let's say, kept two independent sources S1 and another source S2 at x equal to some d like this, okay, on the string. So S1 and S2 are two sources which are creating transverse oscillations along the y-axis. S1 and S2 are two simple harmonic oscillators. Okay. Creating transverse oscillations along y-axis, such that they have amplitudes (1.2 millimeters and 1.6 millimeters). Okay. Then identical frequencies (50 Hz) and are in phase. Both the sources are in phase. So first of all, find k omega lambda for the waves created by S1 and S2. And write the equations for these individual waves. Then second, at a general point P at x equal to x, where x is greater than d, okay, what is the phase difference of y1 and y2? And third part, calculate the net amplitude due to interference of y1 and y2 if d is equal to. So I'll give you some values of d. First, just note down the question up to here. So I'll give you a couple of values of d. Just hang on. So work out the first and second part first. First value is 25 centimeters. The second value is 50 centimeters. Okay, so just if you attempt the question systematically, you will understand how to solve these kind of situations. Okay, just start with the basic information in part 1. Then you will understand how to do part 2 and part 3 quite easily. Yes, Ganesh, that is correct. Correct, very good. The values you have given are correct. So this question covers everything, the basics of wave equation and all that, along with now interference also, and phase difference concept and net amplitude and everything. Correct. Yeah, so Ganesh, you got these things correct. Now, when you write the wave equation, you will immediately understand how to get the part 2 and part 3. Okay, just a minute. I will put up part 3 here so that you can do it together. Just yeah, in phase means that their phase constants are equal, or basically, if you think of them like two simple harmonic oscillators, they are oscillating exactly in phase. And that means they reach the positive extreme together, they reach the negative extreme together. So yeah, in terms of maths, you will say that their phase constants are equal, and by default, you can take it as 0. So source 1 as an oscillator, agar A1 sine omega t hai, then source 2 should also be A2 sine omega t. There's no phase difference between them. By default, you can take that phase term as 0 for both of them. Because you could have started, phase difference is, no, but see, the thing is, by the time the waves are reaching the point P, the sources are in phase. Okay, the sources are in phase, but that doesn't mean that the waves are in phase. So that is where you'll understand the wave equation becomes important. Now, the source S1 is further away from the point P, and the source S2 is closer to the point P. So the waves that are, so that is the important thing. So this question teaches you the relationship between phase difference and what is called path difference. यहाँ पे S1 to P का जो path है और S2 to P का जो path है, उसमें there's a difference of D. Now there's a delta X, there's a path difference. So that path difference creates a phase difference. Even though the sources are in phase, but the waves reaching the point P are not going to be in phase because they're traveling through different paths. So that becomes a very important thing in solving questions. Yes, very good. Samadip, you got the correct answers. Ganesh, you have also got the correct answers. Very good. So 50 centimeters के केस में perfect destructive interference हो रहा है ना. Whereas 25 centimeters के केस में you are getting a phase difference of pi by 2. So getting root of a1 square plus a2 square. So very good. Okay. So let me systematically work out each of these. Okay. For everybody here now. So in the first part, where you have to understand the equation of SHM for each one, first of all. So we will go with that kind of derivational method that we had seen earlier. That ये string है मेरा, इस पे मैंने origin पे एक source attach कर दिया है. So I am forcing the origin point to now oscillate according to the equation of S1. So Y1, the wave created by this at x equal to 0 is how much? It is A1 sine omega t, suppose. I'm just assuming I've started my stopwatch at the time when the oscillation was going through the mean position with positive phase. So this is the source S1 as a simple harmonic oscillator. So the wave it is now creating, this wave is, let's say, Y1. So Y1 as a function of x and t will become what now? It will become A1 sine omega into t minus x by v, or A1 sine omega t minus kx, where omega, by the way, is 2 pi f. So that is over here 100 pi. And because f was 50 hertz, this speed with which this is traveling is square root t by mu, which when you work out will be 50 meters per second. So k will become 2 pi radians per meter, or lambda will become 1 meter. So that is this equation. So just like we've written the equation for the first source as an oscillator first, and then of course we've written the equation of the wave by it. Now similarly we'll do for the second one also. Okay. So the second one is, let us say, sitting at some arbitrary position like this. At x equal to d, we have the second oscillator S2. So S2 का equation क्या है? That is y2 at the point x equal to d. That is some amplitude A2, but sine same omega into t and same phase. Okay. So this is at same frequency and in phase with S1. Okay. So now the wave that this one is creating, that wave as a function of xt will become A2 sine omega into t minus. Now see, at any point like this, at any point p where x is equal to x, the second wave is traveling how much distance? It's traveling less. It's traveling less by d. So it's traveling a distance of. So this is where the understanding of fundamentals is very important. So ये कितना हो जाएगा यहाँ पे? X minus d divided by d, or this whole term can be written as A2 sine omega t minus k into x minus d. So now you can see we've got the two wave equations. So y1 at any given point is A1 sine omega t minus kx, whereas y2 in comparison is A2 sine omega t minus kx plus kd. Okay, so this is the phase difference where omega was 100 pi and k is 2 pi. Like this. Okay. So you can see that now the resultant displacement at a given point is y1 plus y2. So that will become some net amplitude into sine omega t minus kx plus some net phase term. This will be important, where you can see that E net is that E1 square plus E2 square plus 2A1 A2 cos delta phi, where delta phi is now how much? It is TD. It is the phase difference. So if you just subtract this term from this term, you can see that the phase difference is TD. So that is 2 pi by lambda into whatever that distance d is. So this is the net amplitude and this is the phase difference that it's creating. And also when you work out, you will understand that epsilon becomes tan inverse of E2 sine delta phi divided by E1 plus 2 cos delta, because it's just that kind of thing. This is your E net and this is your net phase term. Okay, so up to this step we are not involving the distance d. This is part 1 and 2. We are writing the general equation. Now you come to part 3. So in part 3, the first part, you're taking d as 25 centimeters and lambda, remember, was 1 meter. So your phase difference delta phi is becoming 2 pi by 1 into 0.25 or pi by 2. So you will get this kind of phase. So you will get your net amplitude as this, which will become 2 millimeters, and you will get your phase term as tan inverse A2 by A1. That here will become 53 degrees because E2 was 1.6 millimeters, E1 was 1.2 millimeters. Whereas in your B part, you are taking the distance as 50 centimeters. So you'll get your phase difference as pi. So that will be destructive interference. So you'll get your net amplitude as 0.4 millimeters. And because A2 is greater than A1, you will get epsilon as pi. That also you can understand by making a equivalent phasor diagram kind of. Okay, so this is the wave equation created by the first source. This is the wave equation created by the second source. The sources are in phase, but the wave is traveling through different distance. यहाँ पे x से चल रहा है, यहाँ पे x minus d से चल रहा है. So that's why this takes longer to reach. So that creates a phase difference. Now depending on how much that d is. So in one case d was exactly quarter of a wavelength. So the first wave was behind in phase by quarter of a wavelength. So quarter of a wavelength is the same thing as quarter of 2 pi in phase. So that is nothing but pi by 2. Because one wavelength in terms of phase is one complete cycle of 2 pi. So quarter of a wavelength is 1/4 of a cycle. So in terms of phase, that is pi by 2. Second case, when you take it 50 centimeters, half a wavelength. So half a wavelength is half a cycle. So that is pi. So that's how it's becoming perfectly destructive interference. So when you approach it by this kind of logical manner, it becomes quite easy to understand the concept of phase difference with respect to path difference. Here we can say d is the path difference. Alright people, so with that we conclude today's lecture. I'll send you the notes and some additional questions and things. So make sure that you revise the concept of interference. You are very clear with the definition of interference, coherence of waves, and then this kind of situation. The last example where we have seen how to calculate the phase difference from the given quantities in a given problem. Okay. So we'll continue from this point next time. We'll do more questions on interference, and then eventually we'll look at another type of superposition which results in something called standing waves. So if you're reading ahead from Resnick or some other reference book, You can read up to standing waves next for transverse mechanical waves, because that's what we cover in the next lecture. All right, people. So hope you understood everything properly. That's it from my end for today. Okay. Wish you all the best.